you. So thank you for giving me the opportunity to give this presentation. So today I will present you some results from R Scl based on the work and the observation done with MATISSE. So for those who don't know me, I'm Julian Drevon. So I'm a PhD student. So my home institute is at the Observatoire de la Côte d'Azur at Nice in France. But for my second year of PhD, I have the opportunity to be in the studentship at ISO in Chile. And my PhD supervisor are Pierre Cruzalep, Florent Amilour, Claudia Paidini, and Peter Cicluna. So let's start. So why study evolved stars? So basically, evolved stars are big factories of dust and heavy elements in the universe. So these are just forming the building blocks for forming planets, for forming asteroids, and for forming even life itself. So that's why it's really important to know and to understand better how this kind of building blocks are formed to better understand those kind of formation there. So, our work was based on one of those dust factories, which is called R Scl, which is an AGB star. So here, basically, you have the ID card of R Scl with temperature, luminities, distance, mass, and mass loss. On your right, you have here the complete UV coverage done by the observation of MATISSE of December 2018. And the advantage of MATISSE was, in fact, so like you see on your left here, there was plenty of different observation that has been already been made of R Scl at different scales. So, for example, at large scales with ALMA, where you can see, in fact, those spiral arms, which are usually induced by binary companion, and much closer view made by Pioneer data. And here you have an example of the image reconstruction done by Markus Witkowski and his team. Where you can see barely the photosphere and the close environment of the star. And MATISSE is here to try to, let's say, observe at dense mass in the field of view around the stars. So in order to fill the gap between the two different scales, here you have also the plots of the different periods. So basically what we did is we took data from 130 years of photometric data. And when we do a parallelogram, we reveal that there is in fact two periods, one period of roughly 1 year and one period of 41 years, which is important to spot, I guess, for giving a complete description of R Scl. So our working strategy on this work was first to determine what the chemical composition of the environment. So in order to do it, we first model the central source, the star by Comarc's hydrostatic model. And when we injected this information into a radiative transfer code equation, which is called DUST. The second step, once we have the chemical composition, was to probe the geometry of the environment. In order to do this, we used two different methods. So the first method was to use the mirror image reconstruction. So in first glance, to know if this is a central symmetric object, there claims either any specific structure that we can spot. And in the second time, we also used Rhapsody, which is a 1D intensity reconstruction profile code that I coded during my PhD. And so the advantage of using Rhapsody in complement to Myra is that Rhapsody will use less free parameters and then which induce less problem of non-uniqueness of the solution. And so both are really interesting to use in this kind of objects. So first, our chemical composition. So the Comarc's plus dusty modeling. We have first the classical acidity fitting. So in orange, you have the acidity provided by MATISSE. In blue, you have the ISO SWS spectra, which has been taken at the same pulsation phase and the MATISSE observation, as well as the photometric data in red. And in black, you have the Comarc's plus dusty final SCD spectra. And we can see that we barely reproduce the ISW spectra. The gaps and the difference are mainly present in the in the molecular absorption features. And since Dusty doesn't handle molecules, this was expected. And concerning the geometry with Dusty, so here you have the visibility in L band, the visibility in N band. So in L band, we have a quite bad fit, in fact, which is expected, since in L band you have mainly the information of the molecules and the molecular absorption features. So since Dusty does not handle molecules, that's why. And we have a quite good visibility in N bands comparing to L band also. So that's our first step. And from this, we have this main result. So basically, all the effective temperatures, mass, the carbon-oxygen ratio, etc., and the dust composition are all these results that we've had with Dusty are consistent with what we can find in the literature, to be honest. So that's a good point. Second step, so the MIRA image reconstruction, what kind of environment we're dealing with. So we have two different sets. So we have in N-band and L-band image reconstruction. So in N-band, we can see an orthodontic structure in N-band. So that's quite interesting to spot. And in L-band, we have also, we can see molecular clouds, which have the similar shape as the one we detected with that Marcus detected with Pioneer, for example, in his work. So we remarked that, for example, here at 3.11, where we're inside the molecular C2H2 plus H in molecular absorption features, we can see that the molecular clouds here are roughly the same shape as the one that has been observed a few years ago, with the same kind of holes inside the molecular shape of the clouds. And here you have a comparison with in L-band in the pseudo-continuum, where basically you don't have as that much information regarding spectral information regarding molecules. Like this, you can compare both. So next, Rhapsody. So Rhapsody is stands for reconstructing anchor radial profile centrosymmetric object with discrete rings for astrophysics. So sorry for this, but I'm a huge fan of Queen, and I wanted to call my code Rhapsody, and then I needed to find something which fits with the acronym. So basically, Rhapsody is made of uniform disk, and then concentric rings around. The width and the number of rings are dependent on the angular resolution of your instrument and the field of view, basically. So once you have the geometry of your model, you will associate a flux for each rings. So the specialty of Rhapsody is that we will merge, in fact, the encode transform work with a Bayesian approach. And so we will then generate, we estimate visibilities, and we estimate also radial profiles. So in the visibilities, here you can see that what we call ring, which is Rhapsody model in blue, is fitting pretty well and better than what Dusty can provide. And in red, you have the MATISSE data. And here you can see also that according to MIRA and Rhapsody are quite consistent with each other, comparing to what Dusty can provide also for radial profiles. And in order to have a complete chromatic geometric description of the object at the end. So here are the Rhapsody results. So basically here, what I show you is, so here you have the normal spectra of the flux. And here are the spectra of the intensity profile for each wavelength. Here the blue dashed are the delimitation of the stellar radius. The green lines here represented are delimiting a layer, a distinct layer that we spotted in this study that we will talk about later. And the blue here solid line is Dusty inner radius. So the Dusty inner radius provided by the radiative transfer code Dusty. And the white line here are representing the different artifacts. So basically in L-band, what we can see in the molecular absorption feature C2H2 and in the continuum, if we want to compare both structure, we see that we have interesting things. So we see that there is some molecular things, additional layer here near the CH3 feature, and in the continuum we are roughly the same size as the estimated size of the stellar photosphere. And in N-band and ISIC, but here is what we have. But like I said, and you can see in N-band, since due to problem of dynamic range and angular resolution, we are mainly invaded. We are mainly we see only artifacts, so not that much to say, to be honest, in this band with Rhapsody at least. So here is a summary of the sculptural environment that we saw. So here you have the central part. So you have the photosphere with some molecular clouds with holes made so of CH2 and ICN basically, and then you have an inmost layer of CH2 and ICN, so molecules also. On the top you have what we spot like a distinct layer at CH2, HCN, and maybe made of AMC dusts. And then we have a fuzzy emission made of AMC and molecules, and maybe SIC, but in the study we didn't spot any clear features of any proof of presence of SIC dusts. So to conclude, at the beginning, what we have a target, we have enabled stars, we have some observables, so we have the visibility thanks to the MATISSE observation, we have isospectra, so in the CD. Each observable giving us some information. So for the visibility, we can retrieve the chromatic and geometric description of the objects. And with the isospectra, we have the chemical composition. And then merging this information with different with software like Comrex plus Dusty, we will add these stellar parameters plus the chemical composition. And with Myra and Rhapsody, we will add the geometry of the environments, and where we spot possibly the distinct layer, but no trace of a binary, for example. So the perspective has to build Rhapsody 2.0 to be able to handle elliptical geometry, to applying the method to new GTO targets, and also with targets from the large program of MATISSE, and waiting for more 3D advanced model. And please see the talk from Susan for more information about it. So I would like to thank you for listening, and to all my co-authors also thank you very much. Thank you for your attention.
Thank you, Julian, and thanks to be on time. So we have questions online or over there. No question. Maybe I have one. You say that you are pretty limited by the Dusty software. Do you plan to use another one to simulate the molecule signature or something like that?
Not yet. That's why. So yes, Dusty, as I said, is only handling dusts. So for the molecular information, we need to use other things. I didn't have the time to. So basically, we were happy at this point to have the information regarding the dust and also the geometrical information, which also can give you some information about the structures. But indeed, we didn't use something radiative transfer code, which is also able to handle molecules. But yeah, it is on the roadmap, let's say. And I would like to say also that Rhapsody is an open source code, which is available on GitHub. So if you have any question about it, don't hesitate.
Question.
Yeah, hello, Julian. This is Jacques Tuska from K11. Very nice results. I was wondering, do you have any way to estimate the significance of the detection of the ring that you have with Rhapsody?
Basically, Rhapsody is able to, at least in L-band, we estimated that above 2% of C9 nose ratio, you can detect the structures. So basically, the dynamic range of Rhapsody is 2%.
Okay, and so here you detect that how many? What SNR do you have on this ring?
What, sorry, what is?
What SNR do you have for the ring that you detect?
Good question. I don't have this in mind, but basically it is above 2%. For sure.
Okay, thank you.
No more question? No online? So thanks again, Julian.
You're welcome. Thank you. See you.